In section 9.4, we take a look at the chain rule. In Calculus 1, we had the chain rule to differentiate functions such as f of x equals 2, the square root of 3x minus 2. So the chain rule was used to take the derivatives of compositions of functions. So the square root of 3x minus 2 can be thought of as the square root function composed with 3x minus 2. So in Calculus 1, when we took the derivative of this, we looked into the derivative of the outermost function. In this case, the derivative of the purple function, the square root of x, is 1 over 2 radical x. And then for this argument, instead of writing an x, we took in the original argument that we had, the 3x minus 2. And then we multiplied all of this by the derivative of that argument, the 3x minus 2, which is 3. To consider this derivative in another way, we could have viewed the square root of 3x minus 2 as the square root of u, where u is equal to 3x minus 2. And let's say we call that y. To consider the derivative of y with respect to x, we would take the derivative of y with respect to u and multiply it times the derivative of u with respect to x. The derivative of y with respect to u is the derivative of the square root of u with respect to u, so that's 1 over 2 radical u. And the derivative of u with respect to x, using this equation, the derivative of u with respect to x would have been 3. So these two expressions are exactly the same if we would have gone in and replaced that u with 3x minus 2. When we're working with functions of many variables, we'll use something similar. So theorem. Suppose that we have z being a function of two variables, x and y, and suppose that x is a function of t and y is a function of t. So whenever you want to say that x is a function of t, typically that's how you tell the reader that that's the case. And also for y being a function of t. So what I like to do is draw a tree of dependencies. So here we have our function f of x, y, that we're calling z. And z is a function of x, and it's a function of y. X is a function of t, and y is a function of t. So given this scenario, if you want to compute the derivative of z with respect to t, this will be equal to the partial derivative of z with respect to x times dx dt plus the partial derivative of z with respect to y times dy dt. How come these guys have the curly derivative while these other guys don't? If we're taking the partial derivative of z, consider that z is a function of both x and y. So if you're talking about taking derivatives, you got to be clear about whether you're taking the derivative of it with respect to x or y. That's why we need the partial derivatives, because you could go either way. But if you're going to take the derivative of x, x is only a function of t, so there's no ambiguity. The derivative is just with respect to one variable. So that's why these guys have the curly derivative while the other guys don't.